This session is an attempt to deliver a very qualitative introduction to statistical mechanics as part of the course BS-PH 201. Before we begin, the first question that one may ask is why statistical mechanics? What is the relevance of statistical mechanics for the work of the would-be electrical engineers and electronic communication engineers? I'm coming to the answer. To begin with, what are electrical or electronic components and devices? An electronic component is any physical entity in an electronic system used to affect the electrons or their associated fields in a manner consistent with the intended function of the electronic system. Electronic devices are components that may be active, diodes, rectifiers, transistors, or integrated circuits, or passive, resistors, capacitors, inductors. Electronic devices are interconnected to create more complex electronic equipment such as computers, cell phones, television sets, etc. Device tolerances and changes in behavior with respect to voltage, humidity, or temperature only need to be good enough to ensure that the equipment they are used in continues to operate as intended. And what are electrical or electronic instruments? An electrical instrument is a piece of electrical or electronic equipment that is specifically designed to accurately measure and control various electrical or physical phenomena, for example, temperature, pressure, flow, and so on. Simple electrical instruments may measure and control voltage, resistance, or current, while more complex instruments may measure and control capacitance, inductance, various parameters of complex waveforms, or various other non-electrical physical phenomena. Now, logic gates are fundamental in the design of digital circuits. All transistor types can be used as the building blocks of logic gates. The transistor, for example, MOSFET, JFET, and diodes that we use today are semiconductor devices. Semiconductor devices have replaced vacuum tubes in most applications. A semiconductor device is an electronic component that relies on the electronic properties of a semiconductor material, primarily silicon, germanium, and gallium arsenide, as well as organic semiconductors, for its function. Now, let's talk about relevance. Yes, we can all agree that you may not be going to get a job or have a career in semiconductor device design or manufacturing or packaging. But it's nevertheless something you have to know about as background for any number of other engineering jobs. Just for an example, understanding semiconductor physics is vital so that you can know the limits of what you can do with semiconductor devices, how much current flow, how fast they can switch, what signal distortion or noise may occur in extreme conditions, how to cope with such limitations, how to extend those limitations by cooling or purification or specialized doping or whatever. You can't be a good engineer without understanding the operating capabilities and limitations of the devices and materials you will be working with, and knowing how and why new devices and materials are better. Someone who designs or works with bridges and buildings needs to know a great deal about steel and other materials, and about material behaviors at the molecular level, and how properties and behaviors change under various environmental conditions, and how they change over time. So, it is for an electrical engineer. It is difficult to imagine an electrical engineering job these days which does not involve the use of semiconductors. Any engineer with that responsibility has to understand what is going on inside the devices he is working with. if he is going to get the most out of those devices at the least cost, with the highest reliability and the best manufacturability. And that is true whether you are involved with research and development or design or with testing or field engineering or sales or technical writing or manufacturing or anything else. The reliability of semiconductor devices is a critical step before the commercialization of devices. Most of the semiconductor manufacturing industries critically monitor the physics behind the reliability data of devices to improve the consistency and hence the yield in the production. Reliability of devices means the consistent performance of the devices operated at different temperatures for extended hours of time. Of course, this definition is not general and it depends on the specific application of the device and its limits. For example, aluminium gallium nitride or gallium nitride based heterostructure field effect transistors are most promising devices for RF and power electronic device applications. The devices based on these materials are usually developed on large area silicon wafers. The development of these materials on silicon wafers results in high defect density in these materials. The operation of the devices with such high defect density is no longer consistent. The devices operated for longer times are observed to fail before their lifetime itself. This is where the physics come in. This is where the physics comes in. The reliability physics primarily involves the understanding of the failure mechanisms of the devices. The fabricated devices are generally disintegrated into pieces, and the microstructure of the semiconductor materials involved are critically re-examined at some special points to investigate whether any damage has occurred due to switching of the devices or any new defects are generated to cause the failure. This step is very critical before the commercialization of the device. No, of course one doesn't use such understanding every day, nor once, nor every week. And that is true with everything you, not once, every week. And that is true with everything you study in engineering. It is not put to use constantly, but there are times in any engineering job of any significance when you need to recall Thevenin's theorem or Laplace transforms or how to solve partial differential equation or even Ohm's law. It's all part of being able to call yourself an engineer. As I say, statistical mechanics is part of the curriculum for a very good reason or several good reasons. Quantum statistics, including the Fermi-Dirac distribution as well as diffusion processes, are fundamental to a sound understanding of semiconductor devices. Another important use Another important issue for electrical engineering students is understanding of the mechanisms of noise generation and stochastic dynamics in physical systems, most notably in electric circuitry. Accordingly, the fluctuation dissipation theorem of statistical mechanics is the theoretical basis for understanding thermal noise processes in systems. Later on, these may be reviewed from a signals and system point of view in a way that is readily useful for engineering students and in relation with other areas in the electrical engineering, like courses related to random processes. Now, let's discuss microscopic and macroscopic systems. What is a microscopic system? A system of atomic dimension or of a smaller size is called a microscopic system. A molecule is an example of such a system. A macroscopic, that is large-scale system is one which is large enough to be observable in the ordinary sense. Such a system contains many atoms or molecules. Some amount of solids, liquids, or gases of our daily experience are macroscopic systems. Now, what are macroscopic parameters? Parameters which characterize the system as a whole and not the individual particles which make up the system are termed macroscopic parameters. What would be the examples? Pressure, volume, temperature, electrical resistivity, etc. may be termed macroscopic parameters. When the macroscopic parameters of an isolated system do not change with time, the system is said to be in equilibrium. Now, what does statistical mechanics do? Statistical mechanics aims at studying the macroscopic parameters of a system in equilibrium from a knowledge of the microscopic properties of its constituent particles using the laws of mechanics. It may be noted that thermodynamics does also aim at studying a macroscopic system in equilibrium. Then why do we need statistical mechanics? It is only natural to expect that macroscopic behavior of a system, that is, things that are happening at the macroscopic level, things that we can visualize normally, is the result of what is happening down there at the microscopic level, that is, molecular level. Thermodynamics does not try to explain or justify or establish the macroscopic behavior of the system from what is happening at the microscopic level. Thermodynamics aims at studying macroscopic system in equilibrium from a macroscopic phenomenological standpoint without considering the microscopic constituents of the system. But statistical mechanics aims at studying the macroscopic behavior of a system in equilibrium from a knowledge of the microscopic properties of its constituent particles using the laws of mechanics. Now we will talk about microstates and macrostates. The macroscopic state or the macro state of a system can be specified by quoting the macroscopic parameters and the energy of the system. The microscopic state or the microstate, also called the quantum state of a system of particles, can be specified by quoting the state such as the position, momentum, orientation and configuration of the individual particles. Since a large number of particles constitute the assembly or ensemble, macro and microstates can be correlated by applying statistical methods based on the theory of probabilities. For a given macrostate, a system can have many possible microstates. Let us consider a system of three particles with three energy levels 0, E and 2E. For the macrostate, characterized by the total energy 3E of the system, there can be only two microstates. We can see that there can be only two ways that this system can have total energy 3E. One, one particle in each of the three energy levels 0, E and 2E. That makes total energy 3E. And two, all the three particles in the same energy level E. That also makes total energy 3E. So there can be only two ways that this system can have total energy 3E. Now, what is an isolated system? A system that doesn't interact and exchange energy with any other system is called an isolated system. A microstate occupied by a system without affecting the macroscopic description is called an accessible state of the system. A microstate occupied by a system without affecting the macroscopic description is called an accessible state of the system. By definition, an isolated system is in equilibrium if the probability of its occupying each accessible state is independent of time. A fundamental postulate of equilibrium statistical mechanics, referred to as the postulate of equal a priori probabilities, asserts that an isolated system in equilibrium is found with equal probability in each of its accessible states. Thank you.